Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the second lecture, lecture 2 of our two-port networks. So today we will discuss about Y parameters. Also we will discuss about the condition of reciprocity and symmetricity. So before discussing about reciprocity, it will be better if you have quickly revised through the notes of the reciprocity theorem because it is mainly related with the reciprocity theorem. Of course, I will not explain it over here. This has already been taught to you before from Himanshu. Okay, so let's first discuss about the Y parameters, also known as the admittance parameters. So admittance parameters are basically where my currents are written in terms of voltages. So this time my independent variables are V1 and V2 and dependent variables are I1 and I2. What do I mean by it? So previously, right, in Z parameter, if you remember, in Z parameter, what was the equation? I told you that in Z parameter, my V1 was equals to Z11 I1 plus Z12 I2 and V2 is equals to Z21 I1 plus Z22 I2. So of course, I told you at that point of time that I1 and I2 should not be a function of each other, right? So basically what I meant by that is I1 and I2 should be independent variables. They cannot be dependent with each other. If they are dependent, then obviously Z parameter would not exist, which we have already seen for transformers of each other. So basically my I1 and I2 are independent variables and my V1 and V2 are dependent on what? V1 and V2 are functions of I1 and I1 and I2, right? So V1 equals to some function f1 of I1 comma I2 and V2 equals to some function f2 of I1 and I2. So basically V1 and V2 are functions of I1 and I2. Okay, so yeah, that is what you have seen, basically what you have learned, right? So in this case V1 and V2 are dependent variables. V1 and V2 are dependent variables and I1 and I2 are independent for Z parameter. This is what we have studied till now. In Y parameter, we just flip the equations. So basically, my I1 and I2 can be written in terms of V1 and V2. So that's why my V1 and V2 now are independent variables and I1 and I2 are dependent variable. So keep this in mind that if your V1 and V2 become dependent on each other, okay, then Y parameter would not exist. Y parameter would not exist. So they have to be independent. So it's something like you are you have your father and mother and you have your sister, right? So you and your sister, so you have to be independent of each other, right? Then only you can take care of your father and mother and everyone else around you, basically. Okay, so these guys have to be independent, then only they can take care of their dependents. So I1 and I2, so if they are dependent on themselves, if you and your sister are dependent on themselves, then how can you take care of your father and mother, right? So first you have to become independent, then obviously you will take care of your father and mother. Okay, very bad example, but I hope you get the point. Okay, so yeah, that's why these have to be independent for Y parameters. For Z parameters, my I1 I2 has to be independent. So that is the difference. If they are dependent here, if V1 and V2 are dependent, then Y parameter would not exist. We'll see that just as example. So Y parameter is written over here. They are also known as admittance parameter. Why admittance? Admittance because their unit is in ohm inverse or Siemens. Their units is in ohm inverse or Siemens. That's why they are called as admittance parameter. Okay, and why you might say, sir, why we need Y parameter? Wasn't Z parameter enough? So you have already learned that for all the networks, Z parameter is not defined, right? So for a particular network where my I1 I2 are dependent but V1 V2 are independent, so for those kind of network I can actually use Y parameter to define that network, right? I can actually use Y parameter to define that network, even though Z parameter does not exist, but I can take help of Y parameter. So we need to have options. So everyone likes options in life, right? So you also want options. So either I want the burger or pizza, anything, right? Any option. So if I say no, you have to eat burger only, so you will say no, that you are like putting something on me, right? So you will say I need options. What what I want to eat, I need options. Okay, so say same here, we need options. So that's why Y parameter is used. Okay, and like these things are written here. Why is it used? Y parameters represent the relationship between the currents and voltages at input and output. So we will see obviously, and they are also referred to as short circuit parameters. Why are they referred to as short circuit parameters? I will explain just in a second. I will explain. Okay, so basically, if I come back here, right? So this is my equation. So if I wanted to find out Y11, how would I find out? So what I will do, I will make V2 0 and then write I1 by V1, that will be equals to Y11. So to find out Y11, what I will do is I will make V2 0. So if I make V2 0, my I1 will be equals to Y11 V1. So my Y11 will be equals to I1 by V1. Okay, so that is what my Y11 will be equals to. So at what? At V2 equal to 0. So how do you make V2 equal to 0? So if I have two port networks, okay, I need to copy the two port networks from the previous lecture, that is way back. So somehow if I have the two port networks somewhere, where is it? Okay, here is the two port network, right? Yeah, this we can copy actually. So this if I copy, and I need to go back quite a lot. Yeah, so if you see that I need to make V2 0. How do you make a voltage source or voltage 0? You just simply short circuit it, right? So we will short circuit the port 2. We will not make I2 0, we will make V2 0. So I will short circuit the port 2, hence the voltage V2 will be 0 simply. And what I will do is I will apply a voltage here and measure the current through ammeter. That's it. For Y11. For Y21, again V2 will be 0, so this is gone. So it is I2 by V1. Okay, condition is my V2 is 0. So it is I2 by V1, so V2 is 0. So basically here this will be the ammeter, right? Do remember this direction of the current. What is the direction of the current? The direction of the current is this. Make sure, right? Don't mess up the direction. So direction is inwards, going into the network, not going out of the network, going into the network. So make sure you don't mess up the direction. So in this direction only you have to measure the current. Okay, this is the positive direction. This is the reference direction. Okay, so you measure the current for this same voltage, applied voltage, and the ratio of current and voltage will give you the Y21. Same for the other cases as well. Okay, same for the other cases as well. Like you just have to flip it, right? You will just have to flip for the Y12 and Y22. So what you need to do is, now you will apply a voltage source on the output port or on the port 2. On the port 2. So now V1 will be short circuited, because why? What is my equation? Let's write the equation again. So my I1 equals to Y11 V1 plus Y12 V2. So if V1 is made 0, then only I will be able to discuss about Y12. So Y12 will be I1 by V2 when my V1 is made 0. So if V1 is made 0, of course, if V1 is made 0, that means it is short circuited. It is short circuited. Now I will apply a voltage source here, obviously. I will apply a voltage source here. Okay, I'll apply voltage source here. So from there you can directly see, measure the currents and directly see. Make sure the direction of the currents are according to the reference. Okay, so yeah, like this you can find out the Y parameters, and that's why it is also called a short circuit parameter, because we are short circuiting the output. Previously we were open circuiting the output, now we are short circuiting it. That's why it is called as short circuit parameters. Like same whatever I have told, same thing is written over here. I will not explain. So basically this is known as the input admittance, because we are measuring the admittance of the input side, but there is a condition when the output port is short circuited. So make sure this condition is there, right? It is not unconditional input admittance, right? Unconditional means without any condition, but here we have a condition. We have to make the port 2 voltage 0, so that's why the output port is short circuited. Y12 is a reverse transfer admittance, basically reverse transfer admittance, because we are measuring the voltage I1 current divided by the V2. Okay, again, how do you remember this? So again, same logic, right? Whatever I have explained for Z parameter, same logic applies here, that this Y means it is admittance. If it is admittance, that means it is the ratio of current over voltage. Now first part is sorted. Step 2 is checking the numbers. So this is 1. So this is 1, that means this is the number of the numerator, so it will be I1, and this, the second number is the number of the denominator, so this will be 1. And of course there are conditions. So this is the Y parameter. Y parameter are also called as short circuit parameters. So either we have to make the voltage as 0, right? So either I can make V1 0 or V2 0. If I make V1 0, will I be able to find out Y11? No. So of course I have to make the other term 0, that is V2. So V2 will be 0 here. So this is the basic thing that you need to keep in mind. That's it. Okay, so V1 by I1 by V1, V2 is 0. Okay, so yeah, these are the Y parameters. This is how you remember, like these are the names. Why it is called reverse transfer admittance? Reverse because I'm applying the voltage on the output port and measuring the current here, right? That's why it is called reverse. And it is called forward because I'm applying the voltage here. Not applying the voltage. Why is it called reverse? So yeah, V1 is 0, right? Okay, in this case V1 is 0. Yeah, I'm applying the voltage here or current source here and measuring the current here. That's why it is called reverse, because output port I am applying the voltage and here I am applying the voltage and measuring the current here. So that's why it is called forward. So I'm going forward from the input to the output port. That's why it is called forward. So I'm going forward. That's why it is called forward, and I'm going backwards from output to input. That's why it is called reverse. Okay, so, and output admittance is just the admittance from the output port, but you have to keep in mind that condition is your V1 has to be 0 with input short circuited. So V1 must be 0. Okay, so this is how you find out. And what else is there? So unit of Y parameters is in Siemens, which is reciprocal, and they are used for modeling circuits, so which we already know. So it can be the Siemens, ohms, or sometimes it is written as ampere per volt. This is also a valid unit, or it is sometimes written as this. Sorry, it is not. Siemens is the reciprocal of ohm, so Siemens can also be denoted like this, or it sometimes is denoted like this, ohm inverse. Okay, so all of these are saying the same thing only, like ohm inverse. Okay, so these are the few important points that you need to keep in mind. Also, another important point is your Y parameter. I have already told you the network must have independent voltages, right? What do I mean by it? That means your V1 must not be a function of only V2, or your V2 must not be a function of only V1. Okay, these are the things. And with Y parameter, like the model will be containing a voltage controlled current source. Okay, why voltage controlled current source? Because I can write the current in terms of voltage. So that's why it is a current source but dependent on voltage. So that's why voltage controlled current source. So here it is a like why? Because I can write my current in terms of voltage. So that's why here we use voltage control current source. Now of course this is not the only way to model it. We can model it with a different way as well, but this is one of the way we can model our Y parameter network. Okay, I in terms of voltage, and the same thing I can say in case of a z parameter. So if I go back to the z parameter, let's go back to the z parameter model. So that is the standard model, but of course your network can be modeled using different elements as well. Z parameter model is not unique. Okay, where is the model? Where is the model? Somewhere there was a model, right? Where is the model? Somewhere. Okay, this was at the end. I guess this was at the end in yesterday's lecture only, I guess. Okay, yeah, this was the last, right? So again, if you see your model here, your model contains what? Your model contains current controlled voltage source. Why does it contain current controlled voltage source? Because I have written my voltage, in terms of current in the equation, right? So of course the voltage is dependent on the current. So like it will be a voltage source only because I am pushing some voltage in terms of current. Okay, that's why the model, sorry, it contains current control voltage source. The model contains current control voltage source, and here it contains voltage control current source. Voltage control current source. Okay, where did it go? Yeah, it contains voltage control current source. So I hope you got the point why it contains voltage control current source and why that contains current control voltage source. Now this is a standard model. Now again, I'm just repeating myself that yes, you can model your network differently as well. Okay, y parameter can be same, and you don't have to model it like this. You can model it differently as well. There is no problem. But what I can think is, if someday like they are framing MSQs now, so theoretically if they ask something like this, right, so you understand that for y parameter what kind of dependent source is used, and for z parameter what kind of dependent source is used, because they can frame a theoretical question, theoretical MSQ from this topic, okay, from this particular concept. Okay, so yeah, that's why I'm explaining you all these things. So yeah, that was about it basically. Now one more thing is the relationship between the z and y parameter. So let us discuss about the relationship z and y parameter. Okay, so basic thing is, if I know my z matrix, like I generally, what is the relationship between z and y? So if I have a z, y will be the inverse of this, right? So same thing applies here as well. If I have the z matrix, z parameter matrix, y will be the inverse basically. Sorry, z will be the inverse of y, or vice versa, right? Or vice versa. So if I want to convert from, if I want to go from y to z, this is the conversion that we need to do. If I want to go from y to z, this is the conversion that we need to do, right? So basically I can say, like, what is my z matrix? Z matrix consists of z11, z12, z21 and z22. And what does y matrix consist of? Y matrix consists of y11, y12, y21, y22. Okay, so now this we have learned, right, how to take the inverse. So inverse I have already taught you. So this will be basically what? The main diagonal elements will be swapped. So it will be y22, and of course I have to divide by the determinant of the matrix, delta y. And the off diagonal elements, the sign will change. This will be minus y12, delta y. Delta y is the determinant of the y matrix, and this will be again, sign will be changed, y21, delta y, and this will be y11, delta y. Okay, now what you have to keep in mind is that my delta y cannot go 0. Delta y is not equal to 0. Of course, if delta y is equal to 0, the inverse will not exist. If determinant of the y matrix is 0, of course the inverse won't exist. Then of course you will not be able to find out the z parameter. Okay, so when it can happen that my delta y is equal to 0, when it can happen? So basically, right, if your delta y is equal to 0, that means what? That means, what is the equation? Equation is your I1 equals to Y11 into V1 plus Y12 into V2, and I2 is equals to Y12 Y21 into V1 plus Y22 into V2. Okay, important point is, if you have studied linear algebra, you will know that if the determinant of this matrix, right, is 0, that means these two rows are dependent of each other. That means they have linear dependency. This y11, y12, y22 have linear dependency between them. Then only the determinant will be 0. Basically, this means that my v1 and v2 are dependent on each other. v1 and v2 are dependent variables. Now, if you are not able to understand, don't worry. This you will learn about linear algebra. Okay. Just for now, just take my word that if the determinant is 0, that signifies that v1 and v2 will be dependent on each other. v1 and v2 are not independent. v1 and v2 will be dependent on each other. Okay. Sorry, not v1. Sorry, what do I mean by it? Sorry. My I1 and I2 will be dependent on each other. Okay. Why? Because if the determinant is 0, that means this row and this row has a linear dependence. What do we mean by linear dependence? So when does the determinant of a matrix is 0? So let's say this is 1 2 1 2 2 4. Determinant of this matrix will be 0. Why? Because the second row R2, sorry, if the second row is the twice of R1. So there is a linear dependence. There is a linear dependence between the rows, correct? This I can rewrite here as well, right? So basically this matrix signifies a y parameter matrix. So here my I1 equals to I2, correct? This is my I1 I2, this is my y parameter matrix, and this is my V1 V2. So determinant of this matrix is 0. So now if I rewrite this matrix, this matrix will be I1 will be equals to V1 plus 2v2, and I2 will be equals to 2v1 plus 4v2. So basically what it means is that, what you can directly write, right, the first, like, second row is the 2 multiplication of the first row. So I can directly write I2 is 2 times I1. So this is not good, right? Because if I want to write my admittance parameter, I have told you that for admittance parameter to exist, I1 should not be a function of only I2, or sorry, I2 should not be a function of only I1, or vice versa. But it is happening over here. So of course I can say Z parameters will not exist. Same thing you can understand from determinant of y as well. If determinant of y is 0, then also it means the Z parameter will not exist. Both of them are saying the same thing, but mathematically doing it differently. Okay, does not exist. Okay, so yeah, that was about that basic thing. So now let's see, do Z parameter exist for a transformer? Before that, of course, this I have told you how to go from y to z, how to go from z to y. how to go from z to y. So I have told you how to go from y to z, how to go from z to y. So if I have z parameter, how do I go to y? So what is y? Y is the inverse of z. So same thing, same logic I will apply here again. Y will be the inverse of z, 1 by z. In matrix format, if I want to write, this will be my y matrix and this will be my z inverse. Okay. So now what we can say is, what are my y parameters? So again, y parameters are y11. So if I have z parameters, so how do I go back to y parameters? That is what I am telling you. So this will be y11, this will be y12, this will be y21, this will be y22, and my, again the inverse, right? Inverse is very simple. Z1 like the main diagonal elements will be swapped, so it will be z22 divided by determinant of z minus z12 divided by determinant of z21 determinant of z11 determinant of z. Again the same logic, that if my determinant of z is 0, then of course inverse won't exist, and of course your y parameters also won't exist. So if delta z equal to 0, then inverse won't exist. Okay, your inverse won't exist. So if your inverse won't exist, then how will you basically solve this, right? So here, if inverse does not exist, okay, so if inverse does not exist, what does it mean? It means basically the two rows are dependent on each other. So what are the two rows of z1 and z2? So if I write that my v1 is equals to z11 I1 plus z12 I2, and my v2 equals to z21 I1 plus z22 I2. Okay, so so of course if determinant is 0, that means my v1 is a function of v2, or v2 is a function of v1. And of course you already know that y parameter will not exist, right, if v1 and v2 are dependent of each other. v1 v2 needs to be independent, right? So here of course they are saying the same thing, that y parameter will not exist. Why y parameter will not exist? Because v1 and v2 are dependent of each other, which is of course the first thing that I mentioned, right? They cannot be dependent of each other, they have to be independent of each other. Okay, so yeah, so that we have learned. So now let's find out the y parameter for a few basic networks. So let's say for a transformer, so will the y parameter exist for a transformer? Again the same thing, y parameter will not exist. Why? Because if I write the turns ratio of the transformer, so v1 by v2 will be 1 by n, because 1 is on this side, n is on the other side. So v1 by v2 will be v1 by v2 will be 1 by n, and my I1 by I2, remember this I2 is the port current direction, but actually transformer current is in the opposite direction. This is out I2 dash, so this will be I2 dash divided by I1. This will be what? This will be the opposite side turns, that is 1 by n. Okay, So again, like if you observe that the voltages are dependent, so of course y parameter will not exist, but let's try to find it out. So if I see what is Y11, so Y11 is, if you remember, it is the ratio of current and voltage. So current by voltage, then the first number will be at the numerator, second number will be at the denominator, and of course I have to make the voltage 0. It is a short circuit parameter, so V2 will be 0. V2 will be 0 here. Now I have to make V2 0. So if V2 is 0, what is V1? So V1 is V2 by N. V1 is V2 by N. Okay. So if V1 is V2 by N, that means I can directly, like this equation I can rewrite, this will be I1 divided by V2 by N. Okay. And we are trying to make V2 0. So of course it will tend to infinity. Of course it is not valid. So Y parameter will not exist. You can check for the other ones as well. You will see Y parameter will not exist. So for a transformer, keep this in mind, just for a simple transformer, right? For a simple transformer, the Y parameter and Z parameter won't exist for a simple transformer. But if it is modified with some resistor, then it will exist. That we have seen, that we have seen the example, right? We have already seen the example. Okay. So yeah, so I will write here, for a simple transformer, Y parameter won't exist. Why it won't exist? Because it has a dependent variable, right? V1 and V2 are dependent of each other. Okay, so that you have to be just a bit careful. So yeah, these are the things I think so like one thing I just written here in a hurry about this thing, right? How do you, like, I hope you know how to find out the inverse of Z, and I hope you know how to find out the inverse of Y. This much you know, right? I hope I don't need to explain how to find out the inverse of Y and Z. So yeah, that's why I skipped that portion, like explanation part of that portion, because that is understood that you know how to find out the inverse. So let's solve few more questions. So this is another question again. We saw for a single series element the Z parameter was not existing, right? But here will the Z parameter exist? Here I1 and I2 are dependent on each other, but V1 and V2 are independent. Okay, that's why Y parameter will exist in this case. So we can cross verify this. So what is my I1? So I1, right, is the voltage difference V1 minus V2 divided by the impedance between the voltage. So I1 for the case 1 I am talking, this is for the case 1 and this is for the case 2, circuit 2 and circuit 1. So for the circuit 1, my I1 equals to V1 minus V2 divided by Z. V1 minus V2 divided by Z. What about for current I2? Current I2 is what? Like now this is my reference. So I always write the potential from here first, then I write this one. Okay, this is my style of KCL. Whatever is your style, you write. Okay, ultimate answer will be same. Okay, whatever reference you follow that reference. So this will be V2 minus V1 divided by Z. So this, right, I can further rewrite as I1 is equals to V1 by Z minus V2 by Z, and this I can rewrite as I2 equals to V2 by Z minus V1 by Z. So this I can compare, right? This is Y11. So what is Y11? So from this equations I can compare Y11 will be 1 by z, y12 will be minus 1 by z, y21 will be 1 by z, y21 will be minus 1 by z, because minus v1 by z should be at the starting, right? This will be plus v2 by z. Okay, so this is y22. Now, like I hope you understood like how to find out y parameters. So y parameters will exist here. So y parameters for a single series element exist. Okay, but for a shunt element will it exist? So if you observe, if I write the voltage v1, right, that is exactly equals to v2 because it is in parallel. So v1 is simply equals to v2. So they are dependent. So of course y parameters will not exist, but let's confirm this. But if you remember, the y parameters did exist for the z parameters did exist for this network, right, previously. So that's why we need to have options so that I can uh, write or characterize my network in terms of a parameter. If the z parameter does not exist, I can take help of some other parameter. So here, if you see that my uh, what is the y parameter? So here, right, basically what is y11? Y11 is I1 divided by V1 when my V2 is 0. So I can directly see that my V1 and V2 are same, right? V1 and V2 are same, they are parallel. So V1 is equals to V2. So I can rewrite this equation as I1 divided by V2. So where V2 is 0. So again finite upon infinite, finite upon 0 will be tending towards infinity. So of course y parameter, I can write here y parameter does not exist for a single shunt element. It will not exist. Okay, just be careful regarding that. Now, like now we had so much difficulty to find the z parameter, right? So that this is where also different parameters come in handy, because z parameters for finding this network was very difficult, but you will see how easy it is to find out the y parameters. Why? I will explain the reason also why. Okay, so if I copy this network, we have to find out the y parameter of this pi network, right? So I have this network, so I can write two KCLs, one KCL at this node, another KCL at this node. So KCL at node 1. Okay, so it will be like this potential is V1 only, right? This potential is V1, so it will be V1 minus 0 divided by Z2 plus V1 minus V2 divided by Z1 plus minus I1 equal to 0. Okay, so from here you can directly write your I1 as a function of V1 and V2. So it will be V1, if I take common, it will be 1 by Z2 plus 1 by Z1 and minus V2 into 1 by Z1, and same you can follow for the node 2. Okay, KCL2. So the KCL2 will be very simple here. So KCL2, if I see, it will be V2 divided by Z3 minus the incoming current I2 plus V2 minus V1 divided by the impedance Z1 equal to 0. So it will be basically equals to I2 is equals to the uh, this is equals to V2 by Z3. So this will be this will be minus V1 divided by Z1 plus V2 1 by Z3 plus 1 by Z1. Okay, so this is how easy it is to find out the y parameters. So I just had to write two KCLs. So my y11 will be equals to what? So I can write here ultimately in the next page if I have. So in the next page I can write my y11. So I can directly write the y matrix. So y matrix will be equals to 1 by z1 plus 1 by z2. So it will be 1 by z1 plus 1 by z2. Then I think it is minus 1 by z1. Here also it is minus 1 by z1. So this is the formula basically. I also don't recommend and to remember, and I also don't remember this formula. Okay, but if for a nerd, if some nerd wants to remember it, he or she can remember, of course. So this will be again, this will be 1 by z3 plus 1 by z1. Okay, how to remember this? So basically, right, z1 is always common, right? Z1 is the middle element, so that is common between v1 and v2, so it will always remain, it will always stay with every term. Okay, so z2 is only with the input side, so that's why z2 is here with the input. Z3 is only with the output side, that's why z3 is there, okay, in the z22, and in the z11 z2 is there, and the middle one basically whichever one is the common one that you write. So it is negative of 1 by z1, negative of 1 by z1. Z1 is the common between the port 1 and port 2, common impedance. Okay, so that's how simple it was. So whenever you have KCLs, right, KCLs on the ports 1 and 2, so prefer y parameter. Now, of course, you will say, sir, what if the question asks us to find out the z parameter? So, you know, right, you have already found out y parameter. What will be the z parameter? Z parameter will be the inverse of y parameter. So, this is right, this will be y, capital Y. So, inverse of y parameter. So, this much you can do, right? Inverse of y parameter, this much you can do. Okay, just find out the inverse of y parameter, that's it. Just find out the inverse of y parameter and that's it. Okay, and if you have KVLs, right, in the ports, if you can write KVLs in the ports 1 and 2, that's why it was working in the star network, because I had KVLs. Remember, I had written a KVL equation, two KVL equations in ports 1 and 2. Then we will prefer the z parameter. Okay, so these are the key important points that you should keep in mind. Basically, right, this can be also rewritten in terms of the admittances. So what is the admittance of this? This is y1 equals to 1 by z1, y2 equals to 1 by z2, y3 equals to 1 by z3. Okay, so this, right, can be rewritten in terms of admittance also. So this will be y1 plus y2 minus of y1 minus of y1, then y1 plus y3. So yeah, these are the admittance. This is how you write the admittance. So it is similar kind of to the star network for the z parameter. Okay, so yeah, you can remember it, but I don't recommend remembering it. It's totally up to you. So now we will discuss about this reciprocity theorem. Okay, so let me just drink a bit of water. Now, what is the reciprocity condition? Basically, if the network is reciprocal and if it follows the reciprocity theorem, that means the network, sorry, what I meant is, if the network is reciprocal, sorry, if the if the network follows the reciprocity theorem. Reciprocity theorem. So what does the reciprocity theorem says? Reciprocity theorem. So reciprocity theorem says that if I have two ports, okay, and if I give some excitation in one of the ports and measure the current in other port, now if I swap the places, now if I give the same excitation in the port 2 and measure the current in port 1, the ratios will be intact, ratio will not change. Basically the this, right, V1 divided by I2, whatever is the current in the port 2, voltage in the port 1, and this is V2 voltage in the port 2 and current in the port 1, this ratio will be same. Okay, and is this something familiar to us? Yes, it is. Yes, it is something familiar to us. What is V2 by I1? V2 by I1 is basically Z21. And what is V1 by I2? V1 by I2 is Z12. So that's why I have told you, for the network to be reciprocal, Z12 has to be equal to Z21. Same, you can just take the inverse here. So this will be I1 by V2. I1 by V2 is Y12, and this will be I2 by V1. I2 by V1 will be Y21. So same for the Y parameter as well. So for it to be reciprocal, these two have to be same. Now I hope you remember the reciprocal theorem. Basically, a reciprocal theorem says that inside the network there should not be any independent source, because independent source is there. Of course, I will not be able to, it will not be linear, right? If it is not linear, it will not be reciprocal, and of course the parameters won't exist. The two port parameters won't exist. So there should not be any independent source. Okay. Now for few dependent sources, the network can be reciprocal, but mostly what I can 100% surely say is that if my network contains n contains only R LC elements, if the network only contains RLC elements, then it will be purely reciprocal. It will be always reciprocal, no matter what. Okay. So this one you have to keep in mind. If the network contains only RLC, it will be always reciprocal. That is, your Z12 will be always equals to Z21, no matter what. So let's say you have to find the Z parameters, and you see the network has only resistive, inductive or capacitive elements. Then just find out Z12. You don't have to find the Z21. You can directly say that Z12 will be equals to Z21. So that part is saved. Okay. So you can save calculation time if you know. So for dependent source network, right, if the network, so I will write here, if the network contains dependent sources, then we have to check, check, okay, whether it is reciprocal or not. We have to check whether it is reciprocal or not. Okay. So yeah, this you have to be careful. And what about symmetrical network? Symmetrical network, right? Basically, if I divide my network into two parts from the middle, the left hand side of the network and the right hand side of the network must be identical. Okay, then only I can say that the network will be symmetrical. And if the network is symmetrical, basically my Z11 will be equals to Z22 and my Y11 will be equals to Y22. Okay, if it is symmetrical, then my these are the conditions for symmetry. and for reciprocity the condition is Z21 equals to Z12, Y21 equals to Y12. Okay, so like here the same thing I've written. All passive networks without dependent source are always reciprocal. All purely resistive network are always reciprocal. We use KVL for Z parameters. This also I have told you. We use KCL for Y parameters. Okay, so now let's solve few questions. So this one is the first question. We have to find out the input impedance of the network if the admittance parameter is given. Okay, so the first mistake what you will do is you will think that okay, my Z11, right, sorry, my Y11 is the input admittance. You will say my Y11 is the input admittance, correct? Y11 is the input admittance, that is I1 by V1. So I have to find out Zin. Zin is what? Zin is simply V in divided by I in. Okay, V in divided by I in. And also what is my V in? V in is the input voltage V1, right? Port, this is the port voltage. So V in is V1 and I in is the I1 port current. So it will be V1 divided by I1. Okay, so you will say okay, this is equals to inverse of the Y11 parameter. So Y11 is 1 and you will say it is equals to 1, and you will be totally wrong. Why will you be wrong? I already told you that this, right, this was with a condition. What was the condition? Condition was that my I2 current, sorry, my V2 current must, sorry, V2 voltage will be 0, short circuit parameter, right? V2 will be 0. But this is a unconditional parameter. So Zin is what? Zin is the V in upon I in, that is equals to unconditional input impedance. That is equals to unconditional input impedance. So that is what my Zin is. Okay. So now you can, like, of course we are wrong. So how we can solve it? So there are many ways to solve. So we can solve it like this, that we can use the Y parameter. So what are the Y parameters? Y parameter is I1 equals to Y11 V1 plus Y12 V2, I2 equals to Y21 V1 plus Y22 V2, and I can say from here, like the Y parameters are already given to me, right? 1 minus 1 minus 1 1, 1 minus 1 minus 1 1. Okay, so Y11 is 1, that is V1, plus Y12 is minus 1. So this will be minus of V2. I2 is minus of V1 plus of V2. Okay, so these are my equations. So I have another equation. So my port current is here. Okay, this is my port current. So what is the voltage drop across the resistor? So remember, what is the voltage drop? So this is my V2, right, and this is my V1, correct? So let me not like annotate on this. Let me copy this thing. So another important point to keep in mind is that this is my V2, this is my V1, these are my port voltages, standard port current, always it goes into the network, right? So one thing what you have to understand is what is the drop across the resistor. So current is going like this. So this will be at higher potential plus this will be at lower potential, because resistor can only dissipate power. It can never deliver power. It can only absorb power. So this will be plus minus 2 into I2. So if I apply a KVL here, so my KVL is I always choose the first sign, okay, or intuitively also you can see like this is plus minus, this is minus plus, so obviously there is a negative sign. Intuitively also you can see, if you don't want to see it intuitively, you just write the KVL. So if I write the KVL, what is my standard notation? That I always write the first sign. So I will rotate like this, and I will always write the first sign. So here I encounter negative first, so I will write minus V2. Here I will encounter negative first, so I will write minus 2I2. So this will be minus V2 minus 2I2 equal to 0, or any other way also you can understand that simply this will be negative. So V2 comes out to be minus of I2. Okay, V2 comes out to be minus of I2. So now, right, you will simply replace it in this equation. Okay, not in this equation, sorry, you will simply replace it in this equation. Okay, so you will write your I2 in terms of V1, and then sorry, your V1, yes, we have to replace it in this equation, and from this equation I think we will be able to solve. So now if I replace this value, right, in this equation, so my I2 equals to, sorry, my no, what I have to do, right, I have to replace my V2. So what is my V2 in terms of V1? So this I2, right, I2 is equals to what then? So here I can write I2 equals to minus V2 minus V2 by 2. Okay, and I can write here, I can replace this I2, I can replace this I2 here, right? If I replace this I2 here, this will be minus of V2 divided by 2 equals to minus of V1 plus, sorry, this is, yeah, plus V2. Okay, so I can write my V2 in terms of V1, which I will then replace here, right? So ultimately I will get the ratio of V1 by I1. So this will be V1 is equals to 3 V2 by 2, or V2 equals to 2 by 3 V1. Okay, so V2 I can replace over here. Okay, so this will be I1 equals to V1 of minus of 2 by 3 V1. So I1 is equals to V1 divided by 3. Okay, so from here I can directly write the ratio of V1 by I1. Is there any condition? No, there is no condition, right? Why? How did the condition go away? Because you connected a load. This is 3. So because you connected a load, that's why this is the unconditional, right? How did it become conditionless? Because load was connected. So whenever you connect the load or supply, then it becomes unconditional values, right? Input impedance, all those things become unconditional. So here load was connected, right? Here load was connected. Okay, so yeah, I hope you are understanding. Whenever your supply will be connected, you will also observe that few parameters, like not parameters, few terms will become unconditional. So this is unconditional input impedance Zn. So this is the answer of this question. 3 ohms is the answer of this question. Okay, so now basically let's move on to the next question. So this is the next question basically. So let me just bring up the noise levels, bring down the noise levels. So next question is, we have to find out the Y parameters. Let me drink a bit of water. If I just find out the Y parameters, okay, so how do you find out the Y parameters? There are two ways to go about this. Either you can use z parameters to find out. So method 1 is using z parameters, that is I am giving you as homework. So use z parameters, okay, find out the z parameters, then you write your y parameter as inverse of z parameter. That is the homework. This portion is the homework for you. Okay. And of course I will solve it. You will find it in the notes, but I want you to try it out with yourself, or I can solve it. Okay, let's solve it. Let me solve it anyways. Okay, no, not homework. Let me solve it. Okay, because you are like you were seeing this for the first time, so let me solve it only. So here, right, how to use z parameters. So z parameters you will always have to try and use KVLs. Okay, always try to use KVLs, because here, right, I can see V1 in terms of I1 and this is I0. Okay, these two I0. So what is the current through here? So if I copy this network, so this value will be I1 minus I0, and this value is I2, right? So this value will be what? This value will be 2. This is 2 I0. So one more relationship I can write is that my I1 minus I0 plus I2 is equals to 2 I0. So this is a KCL that I can write. So basically my I1 plus I2 is equals to 3 I0. So my I0, right? I0 is equals to what? I0 equals to I1 plus I2 divided by 3. So this can be changed I1 minus I0. So I0 is I1 plus I2 divided by 3. So this will be 2I1 by 3 minus I2 divided by 3. Okay. And same thing, like if I apply the KVL from here as well, I can do. So I will simply apply the KVL here and here. Okay. So if I apply this KVL, first KVL, so this will be my first KVL and this will be my second KVL basically. Okay. So if I apply the KVLs, so in the first KVL my minus V1 minus V1 plus equals to IO plus IO into 6 equal to 0. So basically my V1 equals to 6 into IO. IO is I1 plus I2 divided by 3. So it will be 2I1 plus 2I2. This is my V1. What about V2? So my V2, if I apply the second, this is the first KVL. Okay. And V2 will be V2 will be second KVL. Okay, KVL 2. So KVL 2, this will be basically this will be, right, this will be this KVL, right? So minus V2, then there is a drop of 4 into I2. So minus V2 plus 4 into I2. Then I have a drop of 12 into I1 minus I0. So now the current direction is opposite, right? I have assumed the current direction to be here. I have assumed the current direction to be here. Okay, but it is opposite. So this is plus minus. So negative sign is there. So of course I will choose the negative sign. That is how I write my KVL. So negative into 12 into I1 minus I0. I1 minus I0 plus same voltage 6 into I0. 6 into I0 equal to 0. Of course, the current direction is this, so this is plus minus, so I will write the first sign. So my V2, so I can write my V2 as 4I2 minus 12 I1 minus 12 I plus 12 I naught plus 6 I naught. So this will be plus 16 plus 18 I naught. Okay, plus 18 I naught. So which is equals to 4I2 minus 12 I1, and I naught is I1 plus I2 divided by 3. So it will be plus 6 I1 plus 6 I2. So your V2 will be equals to 10 I1 and is it 10 I1? No, it is not 10 I1. Sorry. It will be 18 I1. Sorry, not 18. Minus 6 I1, and this will be plus 10 I2. Okay. So this will be your V2. So directly now I can write the Z parameters. Z parameter is what? Z parameter is simply the first equation is 2 2. So this is 2 2 and this is minus 6 10. So what you observe is Z21 is not equal to Z12. So of course it is not a reciprocal network. So whenever there are dependent source, it can or cannot be reciprocal. You have to check. Basically you have to solve, right? You cannot simply write. You cannot simply say whether it will be reciprocal or it will be not reciprocal. Okay. So what I can say is I have to find out Y parameter. So it is very simple, right? Y parameter is the inverse of Z parameter. Okay. So if it is the inverse of Z parameter, you can write here that my Y parameter will be equals to inverse of this matrix. So how do we find out the inverse of a matrix? We divide by the determinant, that is 20 plus 12. So it will be 1 by 32. Okay, outside the matrix, and each this main diagonal elements will be swapped. So this will be 10, this will be 2, and the off diagonal elements, the sign will change. This will be minus 2, this will be plus 6. Okay, so this will be the answer for this question. Now what is the method 2? Method 2, right, is to solve them individually. Solve individually, which we already know. Solve individually. How do I solve it individually? So let us first find out the Y11 and Y21. So let's first find out the Y11 and Y21. So if I have to find out the Y11 and Y21, so both have this common condition that my V2 will be 0. So if V2 is 0, right, simply I will short circuit the output. Okay, does not look good. Okay, so this is where my V2 is 0. So now what I can say is, what is Y11 and Y22? So Y11 is basically equals to I1 divided by V1. Yeah, sorry, I had to cut in between because for some reason I had to take an important call. So as I was explaining, is here I have V1, and can I write this IO in terms of V1? Yes, right. So the voltage across the 6 ohm resistor is V1. So what will be the current across the resistor? Current across the resistor will be V1 by 6. So here, right, the current across, current here is I2, here is 2 I naught. So here current will be what? I2 minus 2 I naught, because 2 I naught has gone out here. I naught is V1 by 6. So it will be I2 minus V2 divided by 3. Okay, so this is my current in this branch. What is the current here? Current here is V1 by 6. What is the current here? I1. So I can directly write a KCL at this node. KCL at this node. If I write a KCL at this node, what I will write is I1 minus plus V1 by 6. Outgoing current is positive and incoming current is negative, minus I2 minus V2 divided by 3 equals to 0. Okay, so from here I can directly write what is my I1 equals to, right? uh, yes, what is my I1 equals to? I'm just checking whether I can write something else as well. Yeah, so I can directly write this. What is my I1 equals to? So my I1 here, my I1 plus I2, I1 plus I2, okay, V2, sorry, this is not V2, right? This is V1, right? I'm sorry, this is V1, V1 only. This will be V1. So I1 plus I2 is equals to minus V1. Yeah, I'm sorry, actually, right? This is negative and this is negative, right? So they will be added basically. I'm really sorry. So this will be plus V1 by 2. I'm really sorry. Okay, so let me apply another KCL in this node. Okay, if I apply another KCL, what is 2 I naught? 2 I naught will be simply equals to I naught is V1 by 6, 2 I naught will be V1 by 3. So if I apply another KCL, so whenever you are going with Y parameters, think of KCLs. Think of KCLs, right? So I2, so if I, this is the KCL 1, this is the KCL 2. So this was the first KCL. Let's solve the next KCL. So if I solve the next KCL, basically here I2 is incoming, this is outgoing, right? I2 minus V1 by 3. So I2 minus V1 divided by 3, and I1 is incoming, sorry, I2 is incoming, I2 is incoming, and this is outgoing, right? V1 by 3 is outgoing, plus V1 by 3. Okay, this KVL is nothing new, right? This we have already, okay, this KVL we have already used, I think. Yes, okay, this KVL we have already used, right? So this we cannot use. No. This KVL we have already used. Anything else we use? That is what I'm thinking. Okay. So anything else? There is only one option left to use a KCL here, because there is no other way to use any KVL. So we can only use a KCL here. Okay, sorry, a KVL. So if I use a KVL in this loop, okay, V2 is anyway 0, right? V2 is anyway 0, so it does not matter. So this will be KVL. KVL will be 4I2, sorry, yeah, plus 4I2 plus 4I2, and this is I2 minus V1 divided by 3 into 12 plus I2 minus V1 divided by 3 V1 divided by 3 into 12 plus V1 divided by 6, that is basically it is equals to V1, right? Plus V1, this whole voltage is V1 only, right? So this will be plus V1 equals to 0. So from here again, this will be 4 minus 4V1 plus V1, so this will be minus 3V1. So 3V1 is equals to 4I2 and 12I2, so it is 16I2, and yeah, that's it basically. Yeah, that's it. So I can write my I2 upon V1 is equals to 3 by 16. If I multiply 2 on both sides, it will be 6 by 32. Okay, this is your Y21. Let's check, right? Let's cross verify. So here, right, it is Y21 is 6 by 32, which is what we are getting here. So whatever we have done is correct only. What about Y11? Y11 is I1 upon V1, correct? So so I can replace this I2. I can replace this I2 here, right? So I2 is equals to 3 by 16 V1. So I can write this equation I1 plus 3 by 16 V1 equals to V1 divided by 2. So my I1 will be equals to This will get multiplied 8, so this will be 5 v1 divided by 16. So my y11 equals to 5 equals to I1 divided by V1 equals to 5 divided by 16. Okay, this is the y11 value. Let's check, right? So if I multiply this by 2, this will be 10 by 32. 10 by 32, which is exactly what we have already found out with the z parameter method. Okay, so like this you can solve. Let's solve for the next one, that is second case, that is where my v1 is equals to 0. So if v1 is equals to 0, right, can I copy this? Can I copy this? Yes. So if v1 is 0, this one will be sorted. So this one is the easier one. If v1 is 0, right, voltage across this resistor is 0, so current also will be 0. So if current is 0, IO is 0. So if IO is 0, this one also will be 0. 2IO will also be 0 amperes. Okay. So if this is 0, same current will flow through here. So basically I can say that my I1 is equals to minus I2. Why? Because no current is flowing through here. So this and these are in opposite direction. So I1 equals to minus I2. This is the first relationship. Next relationship is apply simple KVL. So if I apply a simple KVL, minus V2 plus 4 into I2. Here no current is flowing, so it will be in series. So this will be plus 12 into I2. And here again the voltage drop is 0. So this will be equal to 0. So my I2 by V2 is simply I2 by V2 is 1 by 16. Okay, I2 by V2 is simply 1 by 16. If I multiply 2 on both sides, it will be 2 by 32. Let's verify. So it is Y22, right? It is Y22. Let's verify. So our Z parameters we have there. Yes, it is 2 by 32. Whatever we have found out. So what is Y12? Y12 is I1 upon V2 when V1 is 0. Correct? So I1 is what? I1 is minus I2. So it will be minus of I2 divided by V2. So I have already told you, right? I1 is minus I2. So minus I2 by V2 is, sorry, I2 by V2 is 1 by 16. So minus I2 by V2 will be minus 1 by 16. This will be minus 2 by 32. Let's check. Okay, something, okay, this is correct, right? This is the Y12, that is minus 2 by 32. So we have absolutely done it in the correct manner. Okay. So yeah, that's how you solve basically with individually. If you want to, if I want to write down individually, this is how you can solve. Of course, you can take into the effect of combined. Okay. So method 3 is the solve everything at once with all the unknowns, but that will be very complex. Solve everything at once, but that will be very complex. Okay, so yeah, that is the case over here basically. What else? So I can directly write my y parameter. So y parameter we can safely write. Y parameter will be what? This will be y11 was 10 by 32. Sorry, it was 10 by 32. Yeah, it was 10 by 32. This was minus 2 by 32, and y21 is 6 by 32. And y22 is minus y22 is sorry, 2 by 32. Okay, so these are the parameters basically. This is how you can solve this question. So like, this was a long explanation, but it is required, right? It is required because we are solving this for the first time, so it will take us time, and that is fine. So let's solve this next question. So we have to find the following parameters of the network if the z parameters are given. Okay, remember all these are unconditional parameters, right? This ratio I2 upon I1 is unconditional. How it can be unconditional? Because a load is connected. If let's say this load was not connected and they would have asked you the ratio of I2 upon I1, you will not be able to say, you will not be able to find out. Trust me, you try any method, you try, you remove this 10 ohm and you try to find out, you will not be able to find out the value of I2 upon I1. Trust me, you will not be able to find out. Okay, so without making anything zero. So here these are all unconditional parameters. Okay, these are all unconditional parameters. So you can solve this. How you can solve? So z parameters are given, so I'll write the equations. So v1 is equals to, so I will first of all I will write the port voltages. So port voltages will be here, this will be my plus minus v1 plus minus v2 I1 I2. Okay, and my what I can say is that v1 is equals to 2 I1 plus 4 I2 and v2 equals to 6 I1 plus 8 I2. Okay, and again this relationship is there, so of course your I2 is flowing like this, right? So drop will be somewhat like this will be plus minus 10 I2, correct? Drop is in the opposite direction. So again you can say, you can apply a KVL here on the output loop. This will be minus v2 minus 10 I2 equal to 0. So your v2 is equals to minus of 10 I2. That is what your v2 is equals to. So now you can of course put this here. Okay, we have to find out, first of all we have to find out I1 by I2. So I will solve each one at a time. So if I put this, right, v2 equals to minus 10 I2 here, so this will be minus 10 I2 minus 10 I2 equals to 6 I1 plus 8 I2, and this will be minus 6 I1 equals to 18 I2. Okay, so I1 equals to minus 3 I2. Okay, so I1 is minus 3 I2, so I1 by I2 is minus 3. So this is the first solution, first answer. Okay, this one is the first answer. Oh, okay, they have asked the reverse, sorry, they have asked the reverse. So I2 by I1 will be minus 1 by 3. Okay, let's solve the second one. Second one is v1 upon I1. So I know what is I2 equals to. I2 is equals to minus I1 by 3. So I can replace this in this equation, right, in the first equation I2. Okay, so I will get the v1 and I1 ratio. So we'll copy this. So this one will be v1 equals to 2 I1 minus 4 I1 by 3. So v1 by I1, okay, v1 equals to I1 6 minus 2, so 2 by 3. So V1 by I1 is 2 by 3, okay, ohms. Yeah. So this will be the answer basically, V1 by I1 2 by 3. So 2 by 3 will be the answer, that is Zn, input impedance Zn will be 2 by 3, this will be the answer. Now the second one is I think V1 by V2, right? So V1 by V2 I have to find out, sorry, third one is V1 by V2. So V1 by V2, how do I find out? So V1 I know is I1 into this, okay. So what is V2 equals to? So V2, right, already I have written here, right, the first equation, V2 is minus 10 I2. So I will combine these equations. So V1 is 2 by 3 I1 and V2 is minus 10 I2, minus 10 I2. Also another relationship I know, that I1 by I2 by I1 is minus 1 by 3. I2 by I1 is minus 1 by 3. So what I have to find out? I have to find out V1 by V2, right? I have to find out, sorry, V2 by V1. I have to find out V2 by V1. So V2 by V1, right, will be equals to minus 10 I2 divided by 2 by 3 I1. So it will be minus 5 into I2 by I1. I2 by I1 is simply minus 1 by 3 and divide by 2 is getting cancelled, 1 by 3 is there. So basically it will be 5. So V2 by V1 will be simply 5. So 5 will be your answer for this question, and that is how you solve this question, right? So these kind of questions are not that difficult. I think you will be able to solve it. So this is the last question, I guess, that we have to know. This is not the last question, there are a few more questions left. So this is one of the questions where we have to find out the Z and Y parameters. So okay, similar kind of question only, but here I have a dependent voltage source. Okay, I think somewhere I have done something wrong. This is a dependent voltage source, this is 5V2, so this IO will not stay here actually, this IO will not stay. The rest of the network is same, but IO will not stay. So I have to find out the Z and Y parameters. So if you can find out the Y parameters and then take the Y inverse to find out the Z parameters, or you can find out the Z parameters then take the Z inverse of that, okay, both way works. So I will first find out the Y parameters. Why? Because it is looking like a pi network, right? Pi network, and I have a KCLs looking like a pi network. So if it is looking like a pi network, I will take help of the Y parameter. So I will copy this. This is the method 1. Okay. This is the method 1. So in the method 1, what we will do is we will use the Y parameters. We will take help of the Y parameters. Okay. So this will be the input KCL and this will be the output KCL. So in the input KCL, I have an incoming current of I1 plus the voltage outgoing, that is V1 minus 0 by 2 plus V1 by minus V2 divided by V1 minus V2 divided by 2. Of course there is a voltage source here as well, right? You cannot simply write this equation. So this equation will be V1 and this voltage source is there, so this will be minus of minus 5V2. Okay, so I hope you know how to write the voltage source here, right? So let's say if there was plus minus 1 volt, so I would have written V1 and this potential is V2 node, and another additional plus 1 voltage is there, so another negative sign will come here due to this additional plus 1 volt. So ultimately this point potential is 1 volt higher if this was plus minus, As this is minus plus, so this one potential will be lower. So that's why the signs are opposite of this V2 and V1. So like I'm not explaining you how am I writing the KVL or KCL. Okay, so my expectation is you should be able to write this. Okay, my understanding is you should be able to write this KCL. Okay, that is not my task. Okay, so because that you have already learned in the first chapter. Okay, so I hope there is no doubt in writing the KCLs here. So this will be 5 minus or minus V2 divided by 2. Yeah, that's it. There are only 3 currents, incoming, outgoing equals to 0. So this will be I1 will be equals to V1 divided by 2 plus V1 divided by 2. So this will be V1 and this is plus 4V2 divided by 2, so 2V2. Okay, so from here I directly am able to find out the Y11 and Y12. So let me write the output KCL. So this was the KCL 1. KCL 1. Let's write the KCL 2. So if I write the KCL 2 minus I2 minus I2 plus V2 divided by 2 plus, now this V2 is here, right? The potential drop is happening, so that's why this will be with minus of 5V2. There is a potential drop and this node potential is V1, so this will be minus of V1 divided by 2 equal to 0. So here I can directly write my I2 will be equals to V2 by 2 plus, okay, V2 by 2 plus sorry, minus 2V2, V2 by 2 minus 2V2, so this will be minus V1 divided by 2 minus V1 divided by 2 plus sorry, minus V1 divided by 2 minus, okay, sorry, this will be minus 2 is there, so this will be 3 by 2 V2. Okay, so basically your Y parameters will be your, if I write the Y matrix, my Y matrix will be Y11 is 1, this is 2, this is minus 1 by 2, this is minus 3 by 2. Okay, so this is my Y matrix. So Y parameter we have found out. What about Z parameter? So to find out Z parameter, again you will do the Y inverse, right? As it was almost like a pi network, that's why we went with the Y parameters first. So what is the determinant? It is 3 by 2 plus 1. So sorry, minus 3 by 2. So determinant of Y is minus 3 by 2 plus 1. Okay, so it is minus 1 by 2. So minus, I have to divide by minus of 1 by 2. I have to divide by minus of 1 by 2. Minus of 1 by 2, and this will be, right, this will be plus of, sorry, this, the main diagonal elements will be swapped and the off diagonal elements signs will be changed, so this will be 1 by 2. So if I rewrite this, this will become 3, this will become 1, this will be minus 1, this will be minus 2. Okay, so these are my Z parameters, I guess, if I am not mistaken, right? So yeah, that's about it for the Z parameters. Okay. Sorry. This is wrong, right? This is 4 minus 2 divided by minus half is 4. Yeah, I think everything else is correct only. Yeah, everything else is correct. So these are my z parameters. Now, one doubt students generally have is this network symmetrical? Because what you can do is you can think, okay, this is not the network, right? This is the network. What you can do is you can actually break this network, right? What I can do is you can write, because in the previous lecture also I broken down a resistor, not in the previous, in this lecture only I broken down a resistor, then I told you it is symmetrical. But will that happen here? So this 2 ohm, right, can be on the left hand side and on the right hand side. So if I just try to divide this about the middle, so this 2 ohm can be written as a series combination of 1 ohm and 1 ohm. So this will be 1 ohm and this voltage source also can be divided into a series combination of 2.5 V2 and 2.5 V2. So this will be 2.5 V2 and 2.5 V2. Now you might say that sir, this is symmetrical. You might say sir, this is symmetrical. Actually this is, you might feel like about this point, right, it is symmetrical. It is not symmetrical. It is not symmetrical. Why? Can you tell me why it is not symmetrical? It is not symmetrical because this signs, right, it is not a mirror image, right? It is not exactly a mirror image. Not a mirror image. How it would have been a mirror image? If I would have changed this polarity, right? If I would have changed the voltage polarity, okay, I don't have space. Cut. Let me keep it at the top. If I would have changed the polarity here, okay, this will be plus, this will be minus. Okay, if I would have changed the polarity, then you could have directly said yes, it is mirror image, right? It is mirror image. But you change the circuit. What is the combination of these two? It is 0 volts. The combination of these two dependent voltage source is simply 0, right? Plus 215 minus 215, they are of opposite sign. But that is not my real circuit, right? My real circuit was this one. So of course, yes, it is symmetrical, but it is not my circuit. My circuit is this. So you cannot change the circuit, right? You cannot change the circuit. Of course, you can do few manipulations. Ultimately, final circuit should be remaining same, right? So this is not a symmetrical network. So that can be observed from here as well, right? Your Z11 is not equal to Z22, or your Y11 is not equal to Y22. Okay, so that also you can observe. So another way to solve this is using source transformation. So I'm giving you all the methods. Okay, so if writing this KCL equation, right, is you are feeling bit uncomfortable writing this KCL equation, we have a solution. So what is the solution? Solution is, I will copy this network, is we can use the source transformation. So this is the method 1, just simple KCL. Okay, and method 2 is using the source transformation. Method 2 is using the source transformation. Okay, so source transformation, what you will do with source transformation basically, right? This much you know, right? You can convert a series voltage source with a current source. So this 5v2 can be converted to a current source whose current rating will be 5v2 divided by its internal resistance, that is 2. So 5v2 divided by 2, and the internal resistance will come in parallel with the current source now. So this will be here, and the direction of the current will be going outward from the positive terminal, because it is a source, so it will deliver the power. So it will be going outward from the positive terminal, and this will be same only, and this will be the current source. Okay, so this is the current source basically. This is the current source. So now you can do the same thing, you can apply the KCL. Now it will be bit simpler for you, because now if I apply the same KCL here, right, so you will not have any doubts. So this is 1, this is 2. Okay, so let's write the KCL in the first node. So I1 is the incoming current, then plus this point potential is V1, this point potential is V2. So V1 minus V2 divided by the resistance, plus this is also a outgoing current, right? This is also a outgoing current, this is also a outgoing current. So this will be V1 minus 0 divided by 2, plus this is also a outgoing current. So plus 5 V2 divided by 2 equal to 0. So there are 4 branches, right? This one, this one, this one, this one, 4. So I have written the 4 currents, and the KCL summation is 0. So from here you can directly write your I1 is equals to, it is V1 by 2 plus V1 by 2. So V1, then minus V2 by 2 plus 5v1, so it will be 4v2. So we derive the same thing, right? In the previous method we did the same thing. What about I2? So now if I apply the KCL in the node 2, if I apply the KCL in the node 2, so if I apply the KCL in the node 2, what I will get is, this will be V2 by 2 minus I2 minus R2, then minus current here is incoming, right? Current here is incoming, so it will be minus 5 V2 by 2, and this current is outgoing, V1 minus V2 divided by 2. So sorry, not V1, V2 minus V1 divided by 2. This current is outgoing equal to 0. So now again if you solve this equation, you will find out your Y parameter. So your I2 will be equals to, V2 by 2, V2 by 2. So it will be, okay, it will be minus V1 by 2, okay, minus V1 by 2, and this will be minus 2v2, then plus 2. So this will be minus 3 by 2 v2. So isn't that what we found out previously? Minus V1 by 2 minus 3 by 2 v2, minus V1 by 2 minus 3 by 2 v2. So yeah, you will find out the same value. Just if you are uncomfortable with that, writing this, right, this, so alternative, okay, but you should be comfortable. I think Himanshu has taught you like very good KCL, so I don't think you should be uncomfortable with writing this. Your way can be different because Himanshu may have taken some other reference, okay, but ultimately, right, final result will be same, okay. So because many educators teach the KCL bit differently, everything is correct, but what they have assumed, according to them, they will write the equations, okay. So this is, I guess, the last final question of this lecture. I know it's a long lecture, and I know you have been bearing and listening to me for like almost 1.4 hours or something. I know it's like painful, but trust me, all this pain will come into uh, result once you will get a good rank, right? So that is our ultimate aim. So here we have to find out the power delivered by the 20 ohm, sorry, power delivered to 20 ohm resistor, power delivered to the 20 ohm resistor if the Z parameters of the network is given, okay. So Z parameters are given, right? So again I will write the port values. So basically what is power? Power is power across resistor P20 is I2 whole square into RL, so it will be I2 whole square into 20. So I have to find out I2. I have to find out I2 value. So for that, right, I have to write down the Z parameters. So I know, again I will write down the Z parameters. My V1 equals to 40 I1 plus 60 I2, and my V2 equals to 80 I1 plus 100 I2. Okay, one more thing, again the same thing, right? So this is my V2. I2, right, is not actually this. I was wrong. Sorry. I was wrong. I2 is this. Okay. I2 port current is this, right? And this, let's assume this as IL. Okay, so this will be IL basically. This will be IL. So this will be like I can write my V2 to be minus 20 I2. This we have done in like infinite times previously, so I don't think I have to explain this. V2 equals to minus 20 I2, and you can you can write, you can replace it over here, right? You can replace, and another relationship is there. So this is my V1, right, plus minus V1, and this is my port current I1. So another relationship is there. If I apply a case KVL in the input loop, so if I apply KVL in the input loop, it will be minus 20 plus 10 I1 plus V1 equals to 0. So this will be so I can say that my V1 is equals to 20 minus 10 I1. Okay, so I can replace, first I will replace here I2 V2 value. I will replace here V2 value. V2 is minus 20 I2. So minus 20 I2 equals to 80 I1 plus 100 I2. So this will be 120 I2 will be equals to minus 80 I1. Okay, so 120 I2 will be equals to minus 80 I1. So from here I can replace my I2 in terms of I1. So this will be minus 2 by 3 I1. Okay, this equation, this value I will replace in this first equation. Okay, and also I will replace V1 with this value. So V1 is 20 minus 10 I1. Okay, equals to 40 I1, 40 I1, 40 I1, and I2 is also there, right? So plus 60 I2. I2 is minus 2 by 3 I1. So this will be yeah, this will be 50 I1 and 50 I1 and minus 40 I1. So I1 is 20 by 10. So I1 is 2 amperes. So I1 comes out to be 2 amperes. Okay. Okay. Have I made any mistake? Because my answer is not matching. Okay. Somewhere I may have made a mistake. This is 2 by 3 I1. So this will be 20 minus 40. Okay. Yeah, it is minus 40 only. So it is cancelling each other out. So it is 2 only. So yeah, no, it is correct. I1 will be 2. Okay. I1 will be 2 amperes. That is fine. But I have to find out I2, right? Because yeah, I2, this will be 2, 4 by 3. Yeah. I1 will be 2 amperes. Yeah, fine. I1 will be 2 amperes. What is I2? Because ultimately I have to write the power, right? And power is in terms of IL, and that is negative of I2. IL is negative of I2, right? So I2 is 4 by 3 because it is 2 by 3 minus, sorry, minus of 4 by 3 amperes, and your IL will be negative of I2 because IL is in this direction and I2 is in this direction. So both are opposites, so obviously your IL will be negative of I2, that is plus 4 by 3. So now you can calculate the power, right? You can calculate the power. What will be the power in the load? Power in the load will be IL square R, so 4 by 3 whole square into R is 20. So it will be, I will just quickly calculate this value. So it will be 4 by 3 into 20, 35.55 watts. This will be your answer of the question. So 35.55 watts will be the answer of this question. Okay, this will be the answer of this question. So yeah, that's it basically. Thank you for listening to me for this long period of time, this duration. Obviously, I hope you have taken breaks in between, because I also sometimes take breaks in between. Okay, I also cannot talk continuously for 2 hours long. Okay, so I hope you have enjoyed this lecture. If you did, make sure to hit the like button, and in the next lecture we will start with a new topic, that is H and G parameters. Thank you for watching, and I will see you in the next lecture. Until then, happy learning.